All right, so hello. We're going to be looking at 4.6 today. We're taking notes on rational functions. So our objectives in this section are to, for a rational function, find the domain, graph the function, and identify all of its asymptotes. Then we are going to solve some applied problems that involve rational functions as well. Quick review. What does a rational expression look like? So a rational expression is going to be any expression that can be expressed as a fraction. So for example, we could have the simplest fraction, which would be f of x equals 1 over x, or we could have another fraction where there's a little more going on in the numerator and the denominator. Let's say I've got x squared plus 4 over 3x cubed minus 2x plus 1. I'm just making these up to just give a look at what a couple different rational expressions are. In both of these cases, the key is that you've got a fraction with at least one x variable in the denominator, possibly more, and you can possibly have x values in the numerator as well, as long as you've got a few in the denominator. Okay. So when we talk about a rational function, we mean a function that is the quotient. Quotient, again, is our word for division or fraction in this case of two polynomials. So specifically, we can say that the function f of x equals p of x divided by q of x is a rational function if both the functions p of x and q of x are polynomials and q of x is not just 0. It's going to have something else along with it. Then the domain of that rational function is going to be all of the x values where that q of x function is not equal to 0. So if that q of x function is x, x cannot equal 0. If that q of x function is 3x cubed minus 2x plus 1, that cannot equal 0. And I could solve that and figure out where it was equal to 0 and then exclude those values from our domain. All right. The standard or base parent rational function, whatever word you want to use here, is the f of x equals 1 over x graph, or you can also recognize the f of x equals 1 over x squared graph. In these two graphs, you probably do recognize already the 1 over x graph. The 1 over x graph is characterized by these two separate pieces on the upper right and lower left corner. And there is two sets of asymptotes, or two asymptotes here. So one of my asymptotes is going to be this vertical asymptote at x equals 0. And the other asymptote is this horizontal asymptote over here at y equals 0. All right, so that's a standard graph of y equals, or f of x equals 1 over x. If I look at the graph of f of x equals 1 over x squared, I still have a piece in the upper right-hand side, but on the left-hand side, previously for negative inputs, my outputs were negative. When I plug in a negative value for x, I got a negative value for y. But if I'm going to square that x value, when I plug in a negative value for x, it's going to come back out as a positive. So I have two values, two parts of the curve that have positive outputs. And so this graph does have the same asymptotes. It's also going to have a vertical asymptote at x equals 0. In this case, it's approached on the left and right side, both going up to infinity. None are going down to infinity, but the asymptote is the same line. And we also have that same horizontal asymptote here at y equals 0. All right. So these are two parent functions. You could expand upon this and look for 1 over x cubed. That's going to look very similar to the 1 over x function because the negatives stay negatives, the positives stay positives, and 1 over x to the fourth will look very similar again to the 1 over x squared graph. All right. So on to the next page, we're going to look at the domain of a rational function. Since we know that a rational function is a fractional function, we have a problem when there is a 0 in its denominator, so we need to find those exceptions to what would otherwise be an unlimited domain. So in order to find those exceptions, we need to set the denominator. We don't want it to be 0. We want to make sure that it's not 0. So set it not equal to 0, and then we're going to solve for x. Those are domain exceptions. We do not want there to be a 0 in the denominator. So in example 1, we need to find and state the domain, and we're going to express that domain in interval notation. We really do just care about the denominator when we're looking for a domain, but we do want the denominator in a simplified fraction. So if it's not obvious that the fraction is simplified or in lowest terms, we may need to do some work to get our fraction simplified before looking for the domain. So let's find our domain. So the denominator, we've got ourselves x cubed not equals to 0 to find the domain. And to solve this, we would just raise both sides to the reciprocal power. So we're going to use the 1/3 power, or you could use the cube root if you prefer that notation. That's going to undo exponent 3 as the inverse operation there. So we have that x is not equal to 0 raised to the 1/3 power, which is 0. So this is the domain. This is the domain right here in an abbreviated version of set notation. And we do want to re-express this domain in terms of interval notation. There are going to be plenty of times when leaving it in set notation is fine, but the directions right here ask us to express it as an interval as well. So this would be the interval that includes all numbers except 0, so from -infinity up until 0, not including 0, and then we're going to continue again on the other side of 0, not including 0, up into infinity. So this is the domain, just now written in interval notation. A lot of times when working by hand or on paper, using set notation is just a perfectly fine way to leave it. But it's really important that at least initially, we can go back and forth fluidly between either the set or the interval notation. Let's continue and look at part B. I can see the denominator right here can't be factored, and so I can tell it's not going to reduce with my numerator. So we're going to go ahead and work right from that denominator, and we'll do our 4x minus 3, and we're going to set this to not be equal to 0. From here, I'm going to add that 3 over to the other side. So 4x is not going to be equal to positive 3. Then I'm going to divide by 4, and so I know that x is not allowed to equal 3/4. Okay, so again, that is the domain in set notation. If I want to express that same thing in interval notation, we're going to say we get to have all numbers up to but not including 3/4, and then continuing all numbers from but not including 3/4 up to infinity. So this would be just a way of expressing that same thing. X cannot be 3/4 in interval notation. Okay, let's take a look at the next one for part C. I mentioned the numerator earlier, so we're going to come back and I'm going to make sure we talk about that. But let's begin once again with our denominator. And so our denominator, x squared plus 2x, it is not allowed to equal 0. This is a quadratic, so I'm going to factor GCF of x out. That'll be x times x plus 2, and again, it's not allowed to equal 0. Because it's factored, we can set each factor not allowed to be 0. So x itself is not allowed to be 0, and x plus 2 is not allowed to be 0. So these will give us the two exclusions. X is not allowed to be 0, and when I pull the 2 over, it's going to become x is not allowed to be -2 by subtracting that 2 over. This would be our domain in terms of set notation. We also need to write the interval. So our interval would be from -infinity up to the smaller value I'm going to hit first. That's -2 in this case. So I'm going to go all the way from -infinity to -2, not included. Then we're going to go from -2 until we get to the next solution value, which is 0, not included. And then we're going to go from 0 until there's no more exclusions. So we'll go from 0 all the way to infinity. So this is going to be our domain expressed in interval notation. All right, now I did mention the numerator and what that can do for this as well, and the note at the bottom here is going to play into that. It says there are two domain exceptions or exclusions, but are they causing the same problem? And we're going to find out in a second that the answer to that is no. So let's find out how. So there were two domain exceptions. Those were the 0 and -2. Are they causing the same problem? Let's take a look at this polynomial and see if it simplifies. So I'm going to take the polynomial q of x, and just to keep the top of the page separate from the bottom, you just draw that line right here. I'm looking at factoring x squared minus 3x minus 10. I need to multiply to -10 and add to -3. So I'm going to use a -5 with a +2. X minus 5 times x plus 2. That should be factored. I know that -5 plus 2 is -3, and -5 times 2 is -10. The denominator we already factored, and so that is x times x plus 2. Now what I would like to notice about this right here, is that the x plus 2 factors are on both top and bottom, so those would reduce if I were interested in getting this into lowest terms. That means that the factor x equals -2 is a hole in the graph, because we have that reducing factor. It's a hole in the graph when it comes from a factor that reduces. And the other domain exception, the x equals 0, does not come from a factor that would reduce, so it's going to be the location of one of our vertical asymptotes. Okay, so this other factor is, let me use a different color here. This other factor came from something that did not reduce, so it's going to be a vertical asymptote. This was because the factor does not reduce. Okay, this idea of reducing factors causing holes and factors that do not reduce causing vertical asymptotes is an idea that you're going to study some more in Calc 1. So we're just kind of looking at it right here as a little taste, little preview. And let's go ahead and graph this to confirm. Let me see, I've got a Desmos graph somewhere. Here we go. I want to graph the original function. So q of x here was the fraction x squared minus 3x minus 10 over x squared plus 2x. Oops, x squared, I mistyped that. All right, and let's make this just a little bigger. We can see from this graph here that x equals 0 is a vertical asymptote. And we were suspecting that it was going to be 1 because that 0 did not reduce. But it doesn't look like anything's happening at x equals -2. So x equals -2 is right here. And the graph seems to be connected. But if I hover very carefully, see if I can actually land right on -2. I missed it. Let me zoom in a little bit. There we go. It is undefined. So you can see the hole right there. On the Desmos graph, the pixels are just thick enough that you're not able to actually see the hole, but the graph is undefined. So if you can hover just right, there really is a hole in the graph right here. My hand's shaking a little bit too much to hold it. There we go. So there is a hole in the graph because of that factor that would reduce. So if I wanted to, that looks like that value ordered pair would be -2. Let's see. If that's 2, that looks like it would be about 2.5. Nope, hold on. I don't know what the scale here is. That's 0. That's 1. That's 2. That's 3. Okay, I misread my scale. So if that's 3, that's 3.5. We'll get there one of these times. 3.5. There we go. Just trying here to predict where that point was going to be. And then I could draw that hole there and then actually see the true shape of this graph. Finding out where that hole is supposed to be, finding the output value for that hole is a topic that you'll look at a little bit further into Calc 1. We're just talking right now about the existence of that hole based on having a factor that does not reduce. It's not in the domain, but the behavior at that value is different than the behavior at 0, which is also not in the domain. Interesting. Okay, so more on asymptotes. Look at our topic 2 here. Notice that domain restrictions, we notice algebraically have graphical counterparts, and they are all types of discontinuities of functions. So we've noticed 2 kinds of discontinuities. We've noticed the hole in the graph, and we've noticed the vertical asymptote. Okay, so I'm just going to make a note of this. Discontinuities could be things like holes or asymptotes. Okay. Take, for instance, the following function. F of x is equal to 1 over x minus 3. And let's analyze it for discontinuities. We want to look at this function algebraically, numerically, and graphically. If I look at it algebraically, we're going to start with that denominator again. And we're going to take the x minus 3 and set it so that it is not equal to 0 for the domain, right? So for the domain, we know that x is not allowed to be 3. So this is going to be the set notation way of expressing the domain of this function. So if the domain is a set of x values where x is not allowed to be 3, then there is a discontinuity at x equals 3. We haven't talked about what kind yet, but we know there is one. There is a discontinuity at x equals 3. Now, I actually do know what kind this is based on the fact that x minus 3 as a factor does not reduce with the numerator. So, because it does not reduce, I suspect that this discontinuity is a vertical asymptote, and we're going to confirm that when we go over to the graph in a minute. Let's actually do our graph before we go numerically, make it a little bit easier for us to do the numerical table. So this function, f of x equals 1 over x minus 3. It does appear that there is a vertical asymptote at x equals 3. We'll make that dotted. And from my graph, let's make a little sketch of what we see here. At 3, we've got ourselves that vertical asymptote. Graph is going to go down towards that asymptote from the left side, and then on the right side, it comes down from the asymptote, and then it's going to approach the positive x-axis. Okay, so once again, we see that discontinuity as a vertical asymptote at x equals 3, and so we know that that is a discontinuity, so we can visualize that graphically. If I'm going to visualize this numerically, I would make a table. And I'm going to go ahead and use the function notation I've already built here, f of x, plug x1 into this table. Let's go ahead and get a few rows in the table here. Now, ideally, I would want to figure out what happens at 3. When I plug 3 into the function, it is undefined. So let's see, the middle of this table, I guess there's not really a middle, but I'll put 3 here. And at 3, we know we are undefined. Now we can determine the behavior around 3 by plugging in some numbers that are close to 3. And I'm not thinking 2, which is actually kind of far away from 3. It's a whole unit away. But I might plug in numbers like 2.5 or 2.9 as they're getting closer and closer to 3. So let's say for 2.5, the output value is -2. And for 2.9, the output value is -10. So what we're seeing from these values is that at 2.5, we are at -2. At 2.9, we're at -10. So we're approaching that idea that this graph is going to get very large in the negative direction the closer it gets to -3. And so we're seeing that idea of that vertical asymptote coming out. Let's see if we can get a little closer to it on the other side. So on the other side, if I think about numbers bigger than 3, 4 is definitely too far away. But I might start here with 3.5, and then we're going to get closer. So if I want closer to 3, I could be at 3.1. That's kind of similar to what we did here with the 2.9. It's a 10th away. And I can get even closer and do 3.01. Now it's a 100th away. We're going to get a really big value. So if we start at 3.5, we similarly have that height of 2. So that value is maybe roughly here-ish on my graph. And then I got closer, so I went to 3.1, and this value is 10. Not surprising, lots of symmetry here. So now we're up at a higher height of 10. And if I get really, really close and do, say, 3.01, we see that we are at 100. And so again, so high. And that's really showing that as I get closer and closer to 3, I'm going to have that vertical asymptote. My values are going to grow infinitely large positive and also infinitely large negative on the other side, making that asymptote. So numerically, this is the way that we would be able to show that there was a discontinuity. We're showing that around that value, we get really big negative and really big positive. This idea, again, is explored more in Calc 1, this idea of the table and how do I pick the values to plug in. So we're getting a little bit of a taste right now of limits, actually, of the Calc 1 topic. But we are really going to be focused on the location of those asymptotes, and primarily we'll be finding those algebraically or graphically. Right, so to continue, in general, we say that the line x equals some number, so I'll just say x equals some number a, is going to be a vertical asymptote. The word asymptote is Greek for not coming together, so that's where that word comes from, for the graph of f if any of the following statements are true. The first statement, again, we've got some really formal notation right here. The first statement says that f of x approaches infinity as x approaches a with a little negative in the corner. That little negative in the corner is saying that f of x approaches a from below. So it's not an indication of a negative number, but it's saying I'm approaching the number from the lower side. So for example, if I was approaching 3, from the lower side, my numbers would be getting closer and closer to 3 from below. If we take a look at this diagram over here, we can see that this value right here is the value a. You can see x equals a is where our asymptote is. And we are approaching the value x, getting closer and closer to it from below. Another way to say below, a common way to say below, is from the left, because on the x-axis, the numbers that are below the value a are going to be on the left side of a, And then from above, those numbers will be on the right side. So the negative is for below or for the left side. So our translation here, just going to write this out in words. This means that as x approaches the value a from below or from the left, the y value, which is f of x, approaches positive infinity. So I can write either approaches positive infinity, or I can write that it grows without bound. Two ways of saying the same thing. It is growing to be an infinite value. I'm going to go ahead and use that first version. I'm going to say it approaches positive infinity. So extremely large positive values. So it grows infinitely large. So I've written there in parentheses. Alternatively, we can have a situation where our function approaches negative infinity as x approaches the value a, again, from below or on the left-hand side. So again, we're on the left-hand side of a, and we're going down, approaching negative infinity here. So our translation would be as x approaches the value a from above. Oh, sorry, I'm from below. I'm still up below here because the negative sign right here. I'm already thinking about the next one right here. So from below. So again, we are still on the left-hand side for these first two. We're approaching from below. This time, f of x approaches negative infinity. And that is to say, it grows infinitely small. Or large negative. It is still growing infinitely, so it's going to be infinite, but these values are now approaching negative infinity on the y-axis. Okay, now we're going to approach from above. As we see, this x is going to approach a on the right-hand side above. And so we're approaching positive infinity as x approaches a on the upper side. So this is the right-hand side. So we would read this as x approaches that value a from above. On the x-axis, numbers that are above that value a are on the right side of a, so from the right. In this graph, f of x is approaching positive infinity, so it's going to grow infinitely large. And last, my page didn't print great here, so it's on the next page. Next, we've got the last case right here. Once again, x is approaching a from above, and f of x is approaching negative infinity. So as x approaches a from above, aka from the right side, f of x approaches negative infinity. So it grows large in the negative direction or infinitely small. I actually don't like the phrase infinitely small, so I'm going to rephrase it this time and say infinitely large negative. When I think small, I think close to zero, and I want to emphasize that this is definitely going to negative infinity. So it grows infinitely large in the negative direction. That's probably a better way of phrasing this. In the negative direction. All right. So if any of those four things happens, our graph is going to have a vertical asymptote. Often you'll have two of those things happening. You'll have behavior on both the left and right side of the asymptote. That's going to happen in most of our rational functions. But there are other functions such as the graph of natural log or any logarithmic function, we'll see those in chapter 5, where you only approach on one side and you still have an asymptote. So if any one of these four things happens, that value A is going to be a vertical asymptote. In example 2, our goal here is to find algebraically and state all vertical asymptotes for the following functions. So if we look at the denominators here, we want to find out where our denominators are equal to 0. I am going to set them equal to 0. I'm not using the not equal symbol because my goal is to find the location of the asymptotes, not the location of the domain. So let's take x squared plus 2x minus 8. And let's find out where it is equal to 0. I'm going to factor this. So I need to use a 4 and a 2. The 4 needs to be positive, x plus 4, and the 2 needs to be negative, x minus 2. So that 4 minus 2 is positive 2, and 4 times negative 2 is negative 8. So that gets us factored. Before we continue on this, we're going to check these factors against the numerator. The numerator can't be factored, and the numerator is not going to reduce with either one of those factors. If it did reduce, we'll remember that domain exclusion would be a whole, not an asymptote, and that's not going to occur in this case because neither of these factors reduce. I'm going to make a note of this, that these factors do not reduce. I want to consider that because if they do reduce, it would be an instance of a whole instead of an asymptote. So x plus 4 equals 0 and x minus 2 equals 0 will give us the vertical asymptotes at x equals negative 4 if I subtract the 4 over, and x equals positive 2 if we add the 2 over. So we've got two vertical asymptotes for this function. Now, just for convenience, the graph has already been sketched right here, so I don't need to pull up my calculator. And I can see that there is, in fact, a vertical asymptote at x equals negative 4. And there is, in fact, a vertical asymptote right here at x equals 2. So that's just confirming, if you graph this on decimals or in your calculator, that's the picture you'd see. It's confirming the location of those asymptotes. All right, so we're going to continue on to part B, doing something similar. We're going to take our denominator and we're going to set it equal to 0. I can factor a GCF of x out, so I'll have x times x squared minus 1 equals 0. And then the x squared minus 1, that's a difference of squares, so I can factor that as the x times x plus 1 times x minus 1. And before I continue, I want to check the numerator and see if there are any of these factors that would reduce. So the numerator here, it does look like it factors with a GCF. I could take x out of the numerator and I would be left with x minus 4. So I'm able to identify that there is a factor that would reduce, and it is this factor x. And the other two factors, x plus 1 and x minus 1, are not going to reduce. So it tells me that this graph should have a whole at x equals 0 from this factor. And those other two factors that don't reduce, x plus 1 equals 0 and x minus 1 equals 0. If I solve those, it's going to give me the locations of the vertical asymptotes. Subtract the 1, x is equal to negative 1. Add this 1, x is equal to positive 1. So there's going to be a whole at x equals 0, and there are going to be two vertical asymptotes at x equals -1, and +1. This is a sketch of this graph right here. I can see that at -1, I do have one of my vertical asymptotes, and at +1, I do have the other of my vertical asymptotes. And it's very hard to see the hole. The hole's not going to show up unless I put it there because of the pixels. But the hole must be right there because that is the part of the graph where the x value would be 0. So I've got to have a hole there. It's certainly not an asymptote, even though it is a place where the denominator would be equal to 0. Because it reduces with the numerator, it's going to be the location of a hole. Okay. Let's continue and look at part C here for h of x. Let's take our denominator, x cubed minus 5x, set that equal to 0. We have a GCF of x. If I factor x out, I will have an x squared minus a 5 left over. Unlike the last one, this is not a difference of squares. Unlike 1, 5 is not a perfect square. So we're not going to be able to factor further. If you check the numerator, it's not possible to factor that, and it's not going to reduce with either of these two factors, so nothing reduces here. So I'll just make that note here that the factors do not reduce. Sometimes just writing the note reminds you that I did check it, even though nothing happened to the function. Factors do not reduce. And then I'll set each factor equal to 0. So x equals 0 and x squared minus 5 equals 0. In the x squared minus 5 factor, add the 5 over. X squared is equal to positive 5. And then I'll need to take the square root of both sides. Don't forget that you get a plus and a minus in front of the square root of 5 there. So I have x equals 0. I have x equals negative the square root of 5. And I have x equals positive the square root of 5. So all of these are locations of vertical asymptotes, since none of the factors that they belong to was able to reduce with the numerator. So this graph should have 3 vertical asymptotes. My page didn't print very good again, so it's on the next page right here. But if I take a look, x equals 0, definitely one of the vertical asymptotes right here. The square root of 5, since 5 is bigger than 4, it's going to be just a tiny bit bigger than 2, square root of 4 being 2. So that looks about right here for this asymptote. It's a little bigger than 2. So this would be the vertical asymptote for x equals the positive square root of 5. And then similarly, we're going to be a little bit smaller than negative 2, since the square root of 4 would be negative 2, the square root of 5 is a little bit smaller. So this would be the vertical asymptote x equals negative the square root of 5. So 3 asymptotes matches up with what we see from this function. All right, so let's continue. Taking a look at many of the graphs we've seen so far, it is clear that the vertical asymptotes are not the only kind of asymptotes to consider. Therefore, we also need to define and discuss the horizontal asymptotes. So this graph, for example, seems to have a horizontal asymptote here, as these ends seem to be approaching that central value on both left and right sides. So we're going to talk more about those coming up next. In general, we say that the line y equals b, we used x equals a, so just pick a new letter, y equals b, is a horizontal asymptote for the graph if either or both of the following statements are true. One statement is f of x approaches b as x approaches infinity. So in the graph right here, I can see that as my graph approaches infinity, which is on the far right side of the x-axis, the y values are going to approach the y value b. So if we translate this into an English statement here, we would be saying that on the far right, which is where x approaches infinity, on the far right, that is where x approaches positive infinity for very large values of x, the y values are going to get closer and closer to the value of b. Or the y values approach the value b. And we can also talk about the left-hand side of the graph. So as x is approaching negative infinity, f of x is going to be approaching b. That's talking about the left side of this graph. And again, we can see that y equals b is the value that the graph is coming down there towards. This is going to be on the x-axis where we have those negative infinite values. 0 in the middle, positives on the right, negatives on the left. So on the far left, that's what we mean as x approaches negative infinity. The y values are going to approach that value b. Right. Finding an equation for a horizontal asymptote is not as simple as the vertical variety. For the vertical variety, we're looking at finding where the denominator is equal to 0. For horizontal asymptotes, we're going to need to analyze the function and let the input values get either very positive or very negative. So that's that far right or the far left in order to see what happens to the output. So let's find the horizontal asymptotes for these functions. If we input really big numbers for x, we're going to find that the dominant term in the numerator is going to be the 3x squared term. Imagine plugging in 10. So when you take 3 times 10 squared, that term becomes 300, plus 2 times 10, that's 20, minus 4, these aren't going to have as big of an impact on the numerator as the 3x squared term, the term that has the highest degree. Instead of plugging in 10, plug in 100 or plug in 1,000. When you square 100, you're going to get 10,000 versus a positive 200. The 10,000 is going to eat up the magnitude in the numerator because it does have the highest degree. That's going to happen on the denominator as well. When I plug in those really big numbers, the term that has the highest degree is going to dominate. That's not necessarily true for small numbers, but again, we're only looking for very big numbers. So we just really need to figure out what happens to this function for the leading terms in both the numerator and the denominator. So as x approaches positive infinity, we have really big numbers in both these two positions. So the terms 3x squared over 2x squared are dominant. Here we go. And what happens there is if I look at just those two terms and I reduce the x's out, I can see that the y value here is going to approach the fraction 3/2. So what happens is that as x approaches infinity, that function's output is going to approach 3/2. So 3/2 is going to be the location of the horizontal asymptote here. Now, it also turns out that as x approaches negative infinity, because these are both x squareds, when you plug in a negative infinity to both of them, well, it is going to become positive because of the square. But that doesn't turn out to matter, actually, because I'm going to divide those off, and I'm going to get 3/2 here as well. The only time I might have something different on the y value is if I didn't have the same degree, perhaps, on both sides. Then I might be approaching different things on both sides. But since I have the same degree, x squared, on both top and bottom, I am going to be approaching that same value, 3/2, because the x's reduced out evenly with each other. So on both sides, we have that limit of 3/2. It is possible that we'll have two different horizontal asymptotes, one on the left and one on the right. They don't have to be the same value, but they absolutely are the same value in this case right here. So that means that y equals 3/2 is the horizontal asymptote. So it's abbreviating horizontal asymptote there. There's only one, and we're going to get that asymptote on both left and right sides. All right, so let's take a look at what happens in part B. As x approaches infinity, the term that dominates in the numerator is going to be 2x. If you put in really big numbers for x, 2 times 1,000 plus 3, the 3 hardly matters, right? It's small in comparison to the 2,000 from the first part. So the 2x is controlling the path of the numerator. On the bottom, when you take those large numbers and you cube them, the term of highest degree is going to control the size of the denominator. So if you have a million minus, 20,000, it's going to seem pretty small compared to the million. This one's going to dominate those terms when you plug in values for x. Okay, so the terms 2x over x cubed, which would lead to, let's see, if I reduce this fraction, that would lead to 2 over x squared are dominant. And now, because they're not of the same degree, where I was able to reduce into a single value, I need to figure out what happens to this fraction overall. So in this fraction overall, which of these two is more dominant? Is it the numerator or is it the denominator? After I reduce it, or even before I reduce it, it's clear to see that that denominator was bigger. And we'll think about this fraction in terms of what happens when you take a number like 2 and you divide it by progressively larger and larger numbers. So if you divide it by 10, you'll have 0.2. If you divide it by 100, you'll have 0.02. If you divide it by 1,000, it'll be 0.002. So as x gets large, the values of g of x, this function, are going to approach 0. Okay. Now, we can clarify the way that we're going to approach 0 if we want to. This is something that they talk about in Calc 1, so it's not strictly necessary right now. But I also want to just note that because this is a square, as I approach those positive values, I'm going to be approaching 0 from the top side of 0, so from above. Okay. Now, as x approaches negative infinity, something similar is going to happen here. I'm going to plug in a very large negative number. That very large negative number, once squared, is going to get us a positive value. So we're going to have that same idea of approaching 0. And because the denominator is also coming out to a positive, we're going to be approaching 0 from above as well. So the idea of approaching 0 from above or below is not as important right now as just the fact that we're approaching 0, but just kind of something to think about as you get ready to take Calc 1. So what we know as a conclusion here is that y equals 0 is the horizontal asymptote. Now, I believe if I had this page printed properly, there would be graphs on the bottom of it. For me, they are on the next page. So let's take a look at both of these graphs here and see how that played out with our expectation. For part A, we had y equals 3/2 being the asymptote, and 3/2, this is 1/2, 1, 3/2 is right here. So it looks like on this side that my graph is coming up to approach 3/2. So we're approaching that 3/2 from below on the left side. And over here, we're coming down to approach 3/2. So we're approaching 3/2 from above. Now, I'm adding that post visual right here in the graph. In Calc 1, you'll talk some more about how to determine that algebraically. But we can see from the graph that it is clear that we did approach 3/2 from the bottom on the left, and we did approach 3/2 from the top on the right. All right, now on this one over here, my horizontal asymptote is at 0. And I did mention already the fact that we are approaching from the top on both sides, and that does seem to be the case. And that was because the bottom had that square there, so I was able to just see that the negative and the positive were both going to give me positive values, so I was above 0. Okay, so just confirming, we've got our asymptote, and we even were able to decide how we approach that asymptote. All right. In general, we can say the following about horizontal asymptotes of rational functions. So we talked about how to find them in the last two. We can simplify that just a little bit. In the first case, when the numerator and the denominator have the same degree, that happened in part A, we were able to write the asymptote as y equals the fraction a over b, where a and b were the leading coefficients. Remember, we were able to say that both of these two terms had the same dominance and they had the same degree. So they were going to cancel the x's out evenly and give me that fraction 3/2, which would have been our a over b. That's going to happen every single time we have the same degree. In the next part, if the degree of the numerator is less than the degree of the denominator, it's going to happen the same way as it did in part B every time. If the degree of the numerator is less than the degree of the denominator, once we reduce it, the denominator is going to be the only place that there's a variable, and so that is going to take over as that variable becomes larger and larger, and so the denominator is going to take precedence, shrinking this down to 0. So we're always going to get y equals 0 for our horizontal asymptote if the degree of the numerator is less. The other case is if your degrees aren't equal and the degree of the numerator is not less, then you have the case where the degree of the numerator is greater than the degree of the denominator. And we didn't see an example of that yet because in this case there is no horizontal asymptote. You're only going to get a horizontal asymptote if the degrees are equal or the numerator has a lesser degree. Some important points to consider here. The graph of a rational function will never cross a vertical asymptote. So you can't go through a vertical asymptote. It's a domain exclusion. You can't go through it at all. However, sometimes the graph will cross a horizontal asymptote, but it still approaches the asymptote for extreme values of the input variable. So what we're saying in that example is, like right here, I do absolutely cross 0 right here, and I do cross 3/2 right here. But as the values get larger, I'm going to approach the value of the asymptote. There are even some really weird functions that cross lots of times and then level out at their infinite borders. Okay. And then the last note here is that asymptotes are not part of the graphs of rational functions, but will often draw them in as dotted lines to indicate how the functions behave. So we'll draw in asymptotes to demonstrate an aspect of the function. They're not part of the function itself. Okay, finally, there is a stranger kind of asymptote that is neither vertical nor horizontal. So we're going to look at the asymptote of this equation right here. And we are asked to find all asymptotes. So we're going to start with the asymptotes that we do know. And that means I'm going to start with the vertical asymptote. We do know vertical asymptote, and there is a denominator. So we're going to set it equal to 0 to attempt to find the vertical asymptote. So let's set the x plus 3 equal to 0. The vertical asymptote is going to be at x equals negative 3 as long as that factor doesn't reduce. A quick check back at the numerator shows that it's not factorable. I cannot multiply to a negative 1 and add to a 4. Only way to multiply to 1 is 1 times 1, and that can't add to 4. So it means I am going to get that vertical asymptote. This factor does not reduce at x equals negative 3. Okay. Now, in terms of horizontal, the degree of the numerator is higher than the degree of the denominator, so we know that there is no horizontal asymptote. But there is going to be another type of asymptote. My graph appears on the next page. Yours is probably on the same page. Mine just didn't print very good today. So here's my graph. Let me write in my conclusions here. Vertical asymptote, it is at x equals negative 3. Horizontal asymptote, there are no horizontal asymptotes. I'm going to put none. But there does seem to be something for an asymptote. And this asymptote is diagonal here. So the graph, let me draw in that vertical asymptote as well. That vertical asymptote right here, vertical asymptote at x equals negative 3. The graph is definitely approaching that vertical asymptote, both on the left and on the right as you approach negative 3. But there seems to be something that's diagonal or slant that we're approaching. So we need to find that other asymptote. We're going to find that other asymptote using long division. So let's set that long division up here. We are dividing the divisor, the denominator, x plus 3, into the numerator, into the quotient. So x plus 3 divided into x squared plus 4x minus 1. And if we compute this long division, we'll remember we need to divide x into x squared. X goes into x squared x times. And so if I complete that multiplication and distribute that over, x times x is x squared, and x times 3 is 3x. Then we subtract as part of the long division process. X squared minus x squared is 0. 4x minus 3x is going to be 1x. And we bring down that minus 1, and we do division again. So I'm going to divide x by x. That's going to give me positive 1. Let's multiply again. X times 1, that's x. And 1 times 3 is 3. And we finish by subtracting. X divided by x is 0, and -1 minus 3 is -4. Okay, the results here of my long division have given me the quotient, which is the top part right here, and they've given me the remainder. So I'm just going to write this note right here. This is my remainder. And this is my quotient. And it turns out that the part I need in terms of the oblique asymptote is y equals this quotient. Okay, so we have I'm going to call it SA for slant asymptote. You can also call it the oblique asymptote. So the oblique asymptote or slant asymptote is going to occur at y equals x plus 1. So let's go ahead and check this first before reading the next part of this page. Check this. I know that this is a line with a y-intercept of 1. So there's 1. And its slope would be up 1 over 1, up 1 over 1. So if I graph this, I can go down 1 over 1, down 1 over 1, down 1 over 1. Let's see if I've gotten that right. Looks good. Down 1 over 1, down 1 over 1, and so on. Let me connect these with a ruler. Or actually, I don't need to connect it because it is supposed to be dotted anyway. So it looks like we're not quite as close to it as I was eyeballing in the pink right here. As long as we were able to expand this further, we're going to get closer and closer and closer to that slant asymptote. Okay. That is the slant asymptote. By drawing it in, we're able to confirm that it's in about the right position. And so we are going to have an oblique or slant asymptote whenever the numerator's degree is exactly 1 higher than the degree of the denominator. Whenever the numerator's degree is exactly 1 higher than the denominator's degree. So that did occur in this case. We had ourselves x squared over x. So the degree of the numerator was exactly 1 larger than the degree of the denominator. That's why when I was able to divide these, it came out linear. For that slant asymptote, I was able to divide them. There's a difference of 1 in the exponent. If it's 2 or more in the exponent, you will not have a linear function when you finish the division, so you will not have a slant asymptote. Okay. All right. Continuing on, I'm going to actually make a note here, right here. So we're going to use long division as the method for finding oblique or slant asymptotes. Now, continuing on, if the numerator and the denominator have common factors, we get point discontinuities or holes. Point discontinuities is a more formal way of saying we get those holes in the graph. And these are times when we cancel out domain restrictions, though they never really disappear. Okay. So we talked about asymptotes. We also can talk about the holes in the graph. So take a look at this function. We would have a vertical asymptote at x equals -1 from this first factor. And then because these two factors would reduce, we're going to have a hole or point discontinuity at x equals 2, as you can see right here. This graph also has a horizontal asymptote. I know it has a horizontal asymptote because the degree of the top is 1. If I multiply the degree of the denominator out, it's going to be 2. And if the degree of the bottom is larger than the degree of the top, the horizontal asymptote is going to be at y equals 0. And I can see that happening here. So I can tell all of that just by looking at the equation of this function. Just a note here, typically calculators can't show these point discontinuities, these holes, so we have to check for them algebraically by looking for that reducing factor. Okay, so recap, for any rational function, f of x equals p of x over q of x. Again, this should be on the next page. Hang on a second. Looks like it's on its own. We just need to squeeze everything in on the bottom of my page, and hopefully you've got enough space to write. Discontinuity type. So one of my types, discontinuity, remember, those are only talking about places that are not in the domain. So we're talking about domain exclusions. We're talking about discontinuities. So there are two types of domain exclusion. We have our vertical asymptotes, and those are going to occur when the denominator is equal to 0 and the numerator is not. So the factor does not reduce. So it's going to occur when the denominator is equal to 0 and the numerator is not equal to 0. So that means that their factors do not reduce. Okay, so for a visual on that, we're just going to have some sort of vertical asymptote for our function at wherever that location is. We can picture what a vertical asymptote looks like. The next discontinuity type, I'm going to write out vertical asymptote. I just abbreviated it. The next discontinuity type is the point discontinuity or hole. And this is going to occur when the denominator is equal to 0 and the numerator is also equal to 0, aka the factors would reduce. They have the same solution right here, aka these factors do reduce. And the graph would just have a hole at that value instead of a asymptote. Might have an asymptote somewhere else, but the value in question would be a hole in the graph at whatever that a value is. All right. Topic number 3, we're going to look at some applications now. Because of the features of asymptotes, rational functions are very useful for modeling phenomena that do things like fade away or approach unreachable values over time. In these cases, we keep track of which variables are inputs and outputs as they determine the type of asymptotes present and what they mean in the situation. We also must consider the limits of the situation, i.e. whether negative values are realistic or not. Okay. A couple of examples of real-world phenomena that likely involve asymptotes are heat dissipation from an object coming out of the oven. The temperature is going to drop and then approach room temperature. You would not expect it to continue to drop infinitely, but it would level out at about room temperature. That would be an example of a situation that has a horizontal asymptote. Increases in speed of a particle as it approaches the speed of light. That's going to be another instance of maybe a horizontal asymptote where your particle is going to rapidly increase until it levels out and tries to reach that speed. Population species of organisms in an environment often are going to have some sort of asymptote as well, another horizontal asymptote there. I'm sure you can think of some others. And we'll look again at this first example. Medications usually enter the body, usually the bloodstream via ingestion, and their concentrations are going to vary with the amount of time since introduction. Implant technology allows us to monitor real-time molecular concentration of medication in the bloodstream. This is done for insulin and other medications that you need to be able to measure instantly. And so this is a function that allows us to model the body concentration of N of T in parts per million for a certain medication, whatever this medication is, T hours after ingestion. Okay. According to this function, what was the initial dosage of the medication? So initial dosage is going to be the amount of medication initially taken, so taken at time 0. So I want to find N of 0. When I plug 0 in for T in both locations, that's going to give me 0 plus 1,000 equals 0 plus 4. So it's going to be equal to 1,000 divided by 4. 1,000 divided by 2 is 500. So divided by 4 would be 250. And I think this was in parts per million. That's the units here. So 250 parts per million was the initial dosage of this medication. Okay, that's just the units on that concentration there. What does this function look like for the first 15 hours after the medicine is ingested? So let's get our decimals graph up here. We clear this and enter this new function. So this function N of T is equal to 0.8T plus 1,000 over 5T plus 4. And it's helpful to me to know that the initial value is 250 parts per million so that I can rescale this. I need the Y value to be at least 250, probably bigger. So I'm going to make it 300 just so I'm going to be able to easily see where 250 is. Okay. Now, I don't need to see much that is below x equals 0 because in this context, the medicine is initially taken at time 0. Before time 0, the medicine won't have been taken yet. So this part of the graph is not going to be relevant for this particular situation. So we're going to focus on this portion of the function. All right, so we want to make a sketch here of what the function looks like for the first 15 hours after the medicine is ingested. So we're going to look at it here. So this value at the y-intercept is going to be where we have 250 parts per million. This is our x value, 0. And it drops rapidly at first. We've got 5, 10, 15 will be about here. And we've been asked to look at for the first 15 hours so we can see kind of what the graph is looking like here. Okay. What happens to the concentration for T equals 10, 100, 1,000, and 10,000? i.e., what pattern do you see in the long-term end behavior of this function? So let's go ahead and use a table. And I'm going to use the function n. We're going to input some values into x1 to plug into our function. So let's start by plugging in 10. And just go ahead and keep plugging them in. We want to plug in 100, then 1,000, then 10,000. So what we're getting a sense for here is what the output values are approaching. So 18 parts per million still after 10 hours, but after 100 hours, we're down to 2 parts per million. After 1,000 hours, we're down to 0.3 parts per million. After 10,000 hours, we're down to 0.17998 parts per million. So it might seem like these values are decreasing towards 0, but it's definitely dropping quite rapidly in the beginning and then dropping more and more slowly. So there's very little medication left after that 10,000 hours. Okay, So let me make a quick note of this, and we'll try to figure out exactly what it happens to approach. So the medication drops very rapidly at the beginning. So for the first, say, 2-3 hours, right? 2-3 hours, it drops very rapidly for 2 hours. And by 3, 4, or 5 hours, it already started to slow down. So it drops very rapidly early on. We'll just say early. We know we're meaning in the 0 to 2, 0 to 3-ish range. Then drops more and more slowly until there's very little medication left after 10,000 hours. All right. Mine, again, printed a little weird, so I got to go to the next page to finish off my question. Find and interpret any asymptotes of the function in terms of this situation. So let's look for any vertical asymptotes first. Those are going to be places where the denominator of the function is equal to 0. So I can see my denominator here is 5t plus 4, and that's going to be equal to 0. So 5t would be equal to negative 4, and t would be equal to negative 4/5, or in decimal, negative 0.8. In terms of meaning, this is not going to have any meaning. It's saying 0.8 hours ago, you had an approaching an infinite amount of medication. No meaning, though. That doesn't make sense in this context. So we're going to say this has no meaning because t equals negative 0.8 is before the medication was taken. So we're not able to assign a meaning to the vertical asymptote. We can find it. We can see where it's at on the graph. Not going to have a meaning here. Okay, I'm going to write down my function again right here, just so I can see it since it's on my other page. It should be on your page, so you can just look back and see yours. I'm going to look now for either a horizontal asymptote or a slant asymptote. So first is, which one do I have? Is it horizontal or is it slant? Look at the degrees. So the degree of the numerator is equal to the degree of the denominator. So I know I'm going to have a horizontal asymptote, not a slant. For a slant, I would need to have the degree in the numerator being 1 higher, and that's not the case. Since the degree is the same, I'm going to divide those coefficients. So we're going to have y equals 0.8 divided by 5, just those leading two terms. And that's going to be the location of our asymptote. I'm sure this makes a nice little number. So it comes out as 0.16. So y equals 0.16 is the location of that horizontal asymptote. What does this mean? This means that as time goes on, the amount of the medication in the body is going to drop towards 0.16 parts per million. So over lots of time, the amount of medication drops towards 0.16 parts per million. And this does suggest that there's always some medication remaining in the bloodstream. Eventually, it might become so low that you're unable to register that medication on a blood test, but it is indicating that it's going to be dropping in such a way there's always going to be little left. Now, whether or not that's true depends on a couple of factors. It depends on the model, depends on the medication. This is what our model suggests. And we do know that all models break down eventually. And the further away you get from the data set, the more likely it is that your model has broken down. So if you approach lots of time and let your X get infinite, you've got a very good chance that your model is going to break down. And so over time, it might actually approach zero. Typically, it does with most medications, but this is what the model suggests. That is the meaning of the asymptote. It's what the model suggests. It is then up to the pharmacist or the doctor to decide if that's true, if that medication always remains in trace amounts, or if no, the model has broken down and your body actually eliminates the medication. Without knowing what medicine this is or having a degree in pharmacy, I'm not able to answer that question for this medicine.